Can I start? Hello, everybody. My name is Matsumoto, and I'm willing to serve as the chair for the first IISS this year. And I'm also very pleased to welcome Professor Demura from NIMS as our speaker today. And I sent you the email yesterday that Professor Demura and NIMS are at the forefront of the research utilizing data science. So in his abstract, one phrase is quite impressive. He started his abstract by saying the data age has arrived. So today we look forward to his presentation about these efforts. In addition, I'd like to mention that I²CNER established the Center for Energy System Design in November last year, and Professor Demura is a member of the data science team in the new center. Therefore, not only we can listen to his presentation today, but also we can work together with him at I²CNER and at the new center. And please allow me to introduce Professor Demura's background. He received his bachelor and master degree from the University of Tokyo and then joined NIMS in 1995. And in 2023, he earned his PhD from the University of Tokyo, and he served as a project professor at the University of Tokyo until 2015. And after that, he has been back to NIMS and serve as the deputy director of NIMS Data Science Organization, MADIS. And from 2020, he is the director of MADIS to now. So Professor Demura, thank you very much for giving us your very interesting talk. And if you're ready, I'd like to ask you to start your presentation.
Thank you very much, Professor Matsumoto, for your very kind introduction for me. I'm very pleased to give my talk here. I would like to share my slide now, and so I believe this is now. Okay, so today I would like to talk on the materials research in the data era, NIMS initiatives. So my name is Masahiko Demura from NIMS. And now the NIMS organizations has just been reformed as this April. So my organizations or facilities that from the MADIS to other research network and facility services, I'm directed to this new facility, new center. Okay, so this is a very brief background of the NIMS. NIMS started 2001, joining two national institutes. One is for metal and one is for the inorganic materials. But after 2001, we have welcoming a lot of the organic materials field researchers. So now we're covering large areas of materials science and engineering, from the electronic, optical, energy, environmental, magnetic, structural materials, polymer, nanomaterials, and also we are dedicated to do a lot of effort on the basic research for materials like characterizations and data-driven researches. And the important part is the shared facilities, including fancy facility and also databases and systems for materials DX platform, in which I'm directing these facilities now. And this is the personal informations. We have the 369 tenure researchers plus the 389 fixed term researchers. And also another important characteristics is we have the 72 engineers, tenure engineers, which have the same salary basis on the researchers. And in total, our staff include 1,530. So almost a quarter of researchers from the foreign nations. So we believe materials changes the world and we make the materials. Here I listed two major innovations from NIMS. Here is a silane phosphor materials. And then the right side is the structural materials for vibration damper steels. Both are actually invented and also implemented in the society and used maybe at your home. For example, for this silane phosphor is used in the most of the TV, and also this vibration damper steels are used in this JP Tower Nagoya now. And the interesting thing here is for the case of the silanes, originally this material studies as heat-resistant structural ceramics or materials, which are the promising candidate for jet engine materials. But the researchers at some moment noticed that if they insert the europiums in this cage structures of this oxynitride, so this materials shows a very stable and then high purity materials properties as in a phosphorus. So in this ways, we would like to find the new materials, of course, from the field in this materials field, but also from the other fields. This is very important inventions, I think. So digital transformations are so expected to accelerate the materials R&D. But why we need this? So this is a schematic drawing of the materials research and development. Usually the materials development is to design materials from the desired performance, which is typical inverse problems. So, and also the design space is very huge. So it is very difficult problem essentially. And so usually it is impossible to thoroughly explore because of these too many possible factors. So we have a big expectation that to use the digital transformation technique to make a super rapid research and development in this huge design spaces. So before data era or AI era, we have the experiences or background for data-driven materials researches. So this is the example to develop the NIMS superheat resistant nickel-based single crystal alloys, which are actually used in the Rolls-Royce engine installed in the Boeing 787. So the key point is we have the very nice program to predict the creep rupture time. So this is the NIMS program's performance, and this is the comparable commercial software's predictabilities. You can see that the point predicted by NIMS program is just on this line, which means that the predictability is very high. So the reason of this very precise predictability is the data. We collect the data ourselves through our own experimental facilities, including a single crystalline growth and then the creep experiment. And also we introduce expert knowledge to make very sophisticated formulations to predict this creep rupture time. And another background for the data-driven researches in NIMS is to develop the world-class materials database. We have the 12 different kinds of databases named MatNavi. And for the inorganic compounds, we have the Atom Work Advance, which is the world's largest materials database, collecting the more than 360,000 crystal structures from the academic papers. And for the polymer side, soft matter side, the PolyInfo is world largest or almost only one database in this field. We have already collected 0.5 million data points of properties and more than 20,000 unique polymer structures also collected from the academic papers. In addition to these database from academic papers, there is a database based on the NIMS original experimental data named Kinzok, in which we collected the data for the reliability of metallic materials. So we believe these big backgrounds are very helpful for data-driven researches in this data era. But for our advanced strategies, we decided to take advantage of our own strengths as a materials research institute. We do materials research daily, which means that we generate very high quality experimental and computational data daily. So we decided to collect this data. Then we use this data. So this is completely different from the information science side approaches. That is, we are the Materials Research Institute, so we can do these kind of strategies. So implementing these strategies, we are doing a lot of effort to in these 5 years to develop the systems for the data accumulations and also the tools to use the data here in the scope of the materials data platform. And also we have developed the smart laboratory in which we are doing a high throughput automated experiment. And also we are doing a lot of works relating to the data-driven materials design. So generate data and accumulate data and use or reuse data. All these ecosystems are very important. So this is the system for automatic collections of experimental data in a usable form. Now we have developed a very special systems for these purposes. This is the example of the equipment which are connected to the systems. From these different kind of equipment, we can collect the data daily. So using the materials identifications number, we can use these data very systematic ways. So that this data collections or data structuring systems is named as Research Data Express in RDE in short. And here, the user can upload their own equipment files and also the informations of the materials. And then the system automatically convert this system into the data and also the plotting data and numeric data. And after structuring and compiling data, they are storing in this very sophisticated way. And also, I'd like to emphasize that you can control the people or group who can access this data freely. And in any time, you can change this group or a project or Japan-wide or something. So this kind of the data management system is very crucial for the data era. And regarding the side of the data-driven researches, we have a lot of successful examples. This is a selected example. You can see that the example ranging from the thermal properties and some electronic properties, and then the a kind of the catalyst property, also magnetic property and the metallic powder things, or lithium-ion batteries cases. So for any type of the materials issues, we can apply the data-driven approaches. So this is one example. This example is very important because this is the good example for we use public data to discover new materials. That this here, they would like to develop the world best thermal barriers. They have the idea that the interface between the different elements has a big functions or as thermal barriers. The question is which combinations of elements are effective to get the high thermal barrier functionalities as interfaces. So their team decided to collect the data from the academic paper from the previous works. So more than 1,300 data are collected. And also we use our own database, Atomwork Advance, to get the descriptor information from the for making the machine learning models. And actually, they are successfully making a predicting model in this way. And using this prediction model for the screening machines, they are doing the screening from the more than 80,000 candidates, and they pick up the bismuth silicon pair is promising pairs. And actually, they prove this bismuth silicon combinations gives you the world best, lowest thermal conductivities in these ways. So they are doing, they have done actually the experiment at this last stages. Before this last stages, they are just collecting the data and then doing the machine learning approaches to extract or design the combinations of element, promising combinations. And also we are designing, I'm sorry. So also we are doing a lot of effort for the high throughput automated robotic experiments. This is a case for electrochemistries. So in this movie shows how the robotic experiment working. So first you are making more than 90 different types of the electrolyte. Then they are served to the electrochemical measurement in this way, right? Then you can get the more than 1,000 samples per day, including the combinations of electrolyte and electrochemical properties. Using this automated robotic experiment, these teams are successful to design the new electrolyte for lithium O2 batteries. And in this way, we are successfully, we have a very successful experiences in the data-driven material researches, including the data collections and data generations, and also data-driven materials design. And now I would like to move to a little bit different topics for the digital platform cases for academia industry collaborations. And so this is relating to the national big project in SIP. So here we have proposed a concept named materials integrations. And also we have made the system of the implementations of this concept. The materials integrations is defined as the 2 points. One is the in silico linking among processing, structure, property, and performance. And also we are using data science to integrate experimental data, database, theoretical and empirical rules, and numerical simulations. Simply, you can understand this concept as to replace the experimental centered approaches into the in silico or computational approaches. By do that, you can reduce the cost and time for the materials development. I would like, but not only this kind of side, I would like to emphasize that this kind of idea is very important to revamp R&D system in terms of the academia and industry collaborations. So this is the layer structures from the social issues to the material science. The social issues are reduced into the layer for the needs for materials. And this is the side of the industry. And ideally, these needs for the materials are how can I say, based on the solid basis of the material science. Oh, actually, this layer is a materials engineering layers. So, but unfortunately, now each individual party is each individual issue is handled individually by each players. So this kind of a self-development leads to the situation. There is no accumulation of a problem-solving know-how in the, for example, Japan as a whole. And also it is very difficult in connecting issues and seize technologies. So we decided we need a digital transformation here. So using the concept of materials integrations, in silico linking and data scientific approaches. And so if we can develop the system in which we can accumulate these kind of computer-based solutions, so we can digitally realize the organic approaches between the industry and academia. So we decided to make a specific system named a MINT. So before going to the MINT, I would like to explain in one example. This is the problem of optimization of aging scheduling in nickel-based superalloys. In nickel-based superalloys has two-phase structures, and this is the electron micrograph of these two-phase structures. Here you can see this brighter phases. This is a gamma prime, which is a strengthening phases at the high temperature. So the important point is the size distribution in the volume fractions of this gamma prime. The aging scheduling completely controls the size of the gamma prime. The important things is that if you develop a new materials, you need to re-experiment to reschedule, redesign the scheduling, but it takes a lot of cost. So usually you cannot only do the isothermal heat treatment and you set the temperature and then you just take the aging time as a controlling factor or something. So if you changes this experimental setup into the digital form. Instead of the heat treatment, we are doing the phase field modeling. And then instead of the TM microstructure observations, we can do the image analysis. And also instead of the high temperature experimental testing, we can apply the hardening model to predict the high temperature properties. So we implement these solutions on the computers as modules on these systems, and then connecting these modules into the workflows. And actually, we have already developed such systems, which is a web-based system. So once you implemented the modules, you can freely design the workflow connecting the modules. So here I'm finding the target modules and then drag and drop. And then we are connecting each modules, and now heat treatment modules are added, and then connecting from the initial microstructures. And also now adding a microstructure analysis modules, and then we are adding a high temperature mechanical testing modules and connecting the data. And once the workflows are designed, all the calculations are automatically going ahead. So the information from one modules passed automatically to the next modules. So this is the system of Mint. And using this Mint, you can do the multiple calculation for any types of the aging scheduling. This is summarizations of isothermal heat treatment process map. Using this process map, it is easy to design the optimal conditions of heat treatment. But by experimental methods, it is unrealistic to make such a process mapping. And also we can go further. So using the AI optimizations together with this workflows, we have a chance to design more freely of the aging scheduling. You can heating up and then heating up slowly and keeping or cooling down or something. So we are trying to connect the Monte Carlo tree search, which is one of the very sophisticated AI optimizers. So here is a concept that, okay, let me go back to the layer structures. So if the industry, one of the company has a question that we need to save energy in aging process. Okay, I said, let's make a workflow to design an aging scheduling. And I called to the Professor Koyama in Nagoya University to feed his technology for the phase field technique for this matters. And then I also noticed that, so our colleague, Dr. Osada has a very nice prediction formulations for the high temperature property based on the gamma prime statistics. So I noticed that, okay, we need to create the image processors to extract the statistic information from the phase field simulations. And also I'm asking to Dr. Deep-san to connect these systems to the AI optimizer. So in these problems, the company or industry can use these five top scientists in this field. And not only this, these results are accumulated in the system as in a digital form. So in the same things happen for the different type of the problems. So any types of problems, you can divide it into smaller problems and then connecting these modules as a complete workflow to predict the performance from the process. So in that way, we can accumulate the expertises of various researchers as in a digital form. This is very important. So this is a mint. And now the mint coverage age is widening in the field of the additive manufacturing or high temperature properties or so in this way. And after the remaining time, I would like to quickly show the result of the AI designed or AI inspired experimental design. So this is again the problem of the aging problems. So what happens if you connect the AI optimizer to this mint workflows? So this is the problems. I set the problems. Here's the temperature ranges from 500 to 700. The temperature step is 25. So you have the 9 digit. And in the time scales, you have the 10 steps here. So the searching space is very huge, 9 to 10. And I can't say the big numbers, but this is very big possible scheduling. Okay, so from these ones, what we can select the very nice one. So this is the result of the AI searching. So this is the iteration number. They are trying to find the process which gives you the high proof stress at the target temperatures. And this line is the isothermal heat treatment in the best case. And then very luckily, the AI can find the scheduling which can compete or which can outperform the isothermal heat treatment in here and also here, right? And then the next step is that if you can do this analysis on the computers, we are storing the data in the digital form. So we can analyze after that. Then after this analyzings, we noticed that the very important things from the AI designed isothermal heat, AI designed aging. So this is a top five best performed AI designed aging scheduling. So you can see that this is a common patterns, but this is a very jaggy. So it is very difficult to find the common patterns. But in terms of the gamma prime phase fractions and the gamma prime sizes, we can easily say that in this short time, the gamma prime sizes increase rapidly. And then after these phases, there's almost no changes. And during these time spans, the volume fractions are very gradually increased. So we understand that this first stages, the gamma primes increase rapidly, leading to the high proof stress. And then after these second stages, the volume fractions are a little bit increased. And because of this slight increase, the proof stress is further increased. So from this AI designing, we consider that, okay, if so, we can doing a two-step isothermal aging. In the first step, the short high temperature aging, rapid growth gamma prime up to the best size. And then the second step, long, low temperature heat treatment to suppress the further growing of gamma prime, and then the increased volume fractions. And this is very reasonable according to some dynamic, some stabilities, because the gamma prime is more stable at lower temperatures. So according to this idea, this two-step heat treatment very reasonable. And so we decided what temperature of the second stages is suitable. And then we successfully found that this temperature is best. And then which conditions are supreme, the maximum of the AI founded cases. So this case is very, I think, very beautiful. The AI gives us the possible schedulings or patterns of aging, and then from these solutions, the expert considered deeply, and then which is the intrinsic part. So we can design more, much better solutions, outperforms the AI-based solutions. And also we have another examples based on the Bayesian statistic or so, but today I don't have enough time. So let me wrap up my talk in this way. So now the Japan government decided to build up the materials digital transformation platform, bringing NIMS best practice to Japan as a whole. So this is the same concept we are developed as in the NIMS. So the concept of the materials DX platform is including the data generation part and the data accumulation part and data use or reuse part. And these three parts has their own national project. For the generation part, advanced research infrastructure for materials and nanotechnology projects are now going on. And also the accumulation part, our NIMS take a role of a materials data platform for all of the Japan. We are developed this system on the public cloud. So you can use this platform from the internet. And also the next launches a new materials project for the data creation and utilizations, named DMAT. So this is the last slide. Toward the materials DX platform to increase R&D efficient, we would like to raise the data reuse rate. So here is a materials data platform, and here is a ARIM project. And from ARIM project, the high quality data are coming to the materials data platform, and you can upload your own data, and you can use the shared data, and also you can use the world's largest high quality database by NIMS. And so the important point in this platform is we are preparing its own advanced AI analysis systems, named PNAX. So you can get the solution from this one, from this rich data, and then this DMAT project using this strategy. So this is the last slide. Thank you very much for your kind attentions.
Thank you, Dr. Demura. My impression is that everything is quite new, so it is very difficult for me to understand or digest. But I think audience are understanding more than me. So I'd like to ask the audience to make questions or comments. Anybody is okay? Any questions? Raise your hand, or you can speak to your microphone directly. Toshinori, go ahead.
Yeah, Professor Demura, I thank you very much. So I have one question. Can you hear me?
Yeah.
So go back to one slide. So you are collecting data using the ARIM project, ARIM system. So how do you, I think, how do you pick up so important results from huge data? I think the data collected by ARIM contain so many kinds of results. How do you pick up? So this data is important, and this data is not so important.
Yeah, this is very critical point and very important questions, I think. So actually, the responsibility to do this is the researcher who would like to use the data. So the important point is we are preparing the AI platform on this cloud-based data systems, and in which you can extract the data from the ARIM data and also other data. Then the important things is for the machine learning side, it is very dangerous to confine the data space, for example, in some cases, for many cases. So only the, how can I say, the positive data is not crucial. And the negative data is also necessary to make the nice machine learning modeling. So essentially, it is better to use all the data, but of course, depending on the, how can I say, the applying problems, and then depending on the searching space, of course, you should collect the data. But anyhow, I explained first, the first responsibility is the researcher who would like to use the data.
Okay, thank you very much.
Did there any other questions? So, Professor Demura, may I ask you, so I'm yet try to understand your presentation, but in your presentation, firstly, the accumulation of the data is important. So once you received, or the database can contain many data, and researchers can use the data for the, how do you say, processing or prediction or something, right?
Yes, so I'm sorry, I can't catch your point.
So my point is that, so in the case of data science, data is the first, and then from data we can predict the new material, or we can optimize some property. And in this case, so my question is, so I understand roughly about the collection of the data, and for the collected data, then what you will do for, or researchers have some, how do you say, equipment or some system to utilize the data for their own purpose, or you will provide as well the prediction from the data for specific properties or specific purposes.
Yes, it depends on the, how can I say, the skills or needs of the researchers. So if the researchers has some good skills for the machine learning or data analysis, or sometimes the computational simulations or so, I think for them, the important things to how to feed the data, high quality data, and then how can I say, give the place for the analysis in which you can freely use the data. So, and then other side, I mean, so the materials researchers, and they don't have enough experiences for the machine learning or data-driven researches, we would like to, we have a plan to prepare the very easy, how can I say, very user-friendly interface analyzers of data. So in this kind of how can I say, the tools for AI will be implemented on the PNAX systems. So so we are targeting both sides. One is the expert of the programming and data science or something, and other one is the non-expert one who has an only interested to the material science. So, so for both sides, we are preparing the tools and the place to use the data and then data scientific approaches.
Okay, so another question is that so I let me get Professor Kunitake, thank you for joining. Please make your questions.
Can you hear me?
Yes.
So my question, maybe somewhat related to the previous one, but when the important point is you have a set of data and a set of different kinds of data. So you have to use the kind of data, the proper data, which may be related to the materials properties. So you need very much of the expert knowledge in starting this whole process of this data-driven developments. And so, how much you need? Don't you need the highest level of materials scientists to start with to make a good use of the data provided by the mathematicians?
Yeah, I know it's very, very good questions, I think. So at this moment, you need a deep understanding of a material science and then on this topic. Otherwise, it is very difficult to extract the useful information. So I mean, the data scientist only is difficult to tackle with the materials design problems, even if using these systems. So it is necessary to do the collaborations with the materials expert in this domain. Yeah.
Okay, thank you very much. And one more question. What is the possibility of applying this system to the organic system, organic materials? That's more complex. They are more complex in structure and properties.
Yeah, actually, so my expertise is in inorganic type materials. So I don't have a rich experiences, but my colleague in the field of the organic materials enjoying to use the data-driven approaches, including the machine learning. So step by step, they are, how can I say, developing tools to expressing the structures of the very complicated organic structures, and then the way to predict the property from the organic structures. So I believe the organic, even for the organic materials, you can use these approaches.
Thank you very much.
Yeah.
Thank you, Professor Kunitake. So Lin is waiting. So Lin, can you make your question?
Yes, I'm very happy to hear that. To know that you have to.
Okay. So can you hear me?
For organic materials.
Hold on,
Thank you
please,
very much.
Lin. Okay, Lynn, go ahead.
Yes, thank you for the interesting talk. I very impressed by the work discovery of world-based thermal barrier by using public data from 85 papers. As I understand, the data come from different sources or come from different research group, may result from different computational methods or different experimental setting. So my question here is that how can we normalize the data sample to make them comparable before changing into machine learning model?
I see. So this is also a very difficult problems. So we don't have the complete solutions for this problems. For step by step, or for the, how can I say, the target by target, we are using different techniques. So, but essentially the important point is to keep the reproducibility of the data. So we are designed data collecting workflows along with the research pipelines. So please imagine that what kind of information is necessary for reproducing the result or data. So imagine this kind of things, and we design the workflows of collecting the data. So sometimes we ask to the researchers to fill the enough informations for the as a metadata, what's kind of a material or who are doing this or something. And then also we extract the meta informations for the measuring equipment files. Usually the measure equipment files including the measuring conditions as a header part.
Yes.
And then we automatically extract the this information from the measuring files from the equipment. So we are discussing with the equipment companies, what is the meaning of this matter, and what is the meaning of this, and what is the unit of this numbers or something. So we are, how can I say, using these informations to translate into human readable and machine readable form as a meta informations.
Okay, so as I understand that this type of step need to do manually, problem by problem. That is, there is no no universal methods for normalize the data coming from different source.
Right.
Yeah,
at this moment, so we need to do the tailor-made approaches for each experiment or each research pipelines.
Okay.
So, but once you establish one pipelines for this specific research topic,
Yes.
and you can repeatedly use this pipeline to collect the data, and then so this data is has a guarantee. There's a guarantee for this data that this data is collected in some definite rule. So after that, so the other people can understand the meaning of the data or the reproducibility of the data. So there is a way, we believe, to collect, to reuse the data.
Okay, yes. Thank you very much for the answer. Thank you.
Thank you very much.
So Dr. Kurosawa, you are raising your hand. Please go ahead for your question.
Okay, can you hear me now?
Yes.
Okay, so thank you very much for a very comprehensive talk. So I have learned a lot. So in my understanding, the R&D efficiency have drastically improved in terms of the speed and accuracy and the cost. So my question is maybe you can use these system for the new finding of the new combination of the element or structure in the specific purpose materials, and recently critical minerals have a big social concern we have. So is there any possibility to restrict the overuse of critical minerals in design, especially for the renewable integration of specific material? Do you have some example for that?
Actually, so it is possible to give the constraint, these conditions as a constraint for searching inversely. So I don't have the exact examples, but close example is to use a MINT systems to design the new steel materials, which is cost effective. So the company give the constraint of the cost. The cost is the functions of each element. So if you changes this constraint functions, depending on the critical element or something, so you can do the same things.
Okay, is there another possibility? So very interesting. Thank you very much.
Thank you.
So Professor Kunitake, your hand is yet raised. So do you have another question or? Okay, so Professor Demura, can I ask you one more question? And you showed in your earlier part the database, and right now you are showing the materials DX platform. And is it public? In other words, free of charge to use, or it will be charged, or some limited people can access to this platform?
Okay, good question. So for the database, we open this database as a reference. So we didn't feed a bunch of the data set. So once I allow to download a bunch of the database, the value of the data is lost easily. So we don't allow user to download the data, but we open the data as a reference. So through the web-based application. So I mean, if you can search something and then you can check the value, or you can check the structure or something one by one.
I understand.
Okay. So, but for this platform, you can use the bunch of the data, the as a data set. So, but of course, then you are saying that you need to pay the money or something. So at this moment, this is a free charge. So yeah, and then but this is under construction actually. So now a PNAC systems is under constructions. So maybe we need 1 year for opening a beta stage of this PNAC systems. And then anyhow, at this opening of the beta versions, we don't have a plan to take money from the users. Of course, you need to register, and then we need to do some engagement to how can I say, license agreement or something, but you can use anyhow.
So I don't think if it is a suitable question, but this platform is based on the subsidy from Japanese government. And perhaps the intention is to accelerate the data science in Japan. At least the part of the purpose is the promotion of the data science in Japan. But in this case, I'm Japanese, and if I try to register as the user of the platform, you will accept, maybe. But for example, what will you do from the registration from the foreign countries? So the users from the foreign countries can use this platform equally with the Japanese people.
Good point. So at this moment, we don't have any plan to open to the people from the foreign countries. Yeah. So of course, one reason is the purpose to develop this platform is to enhancement of the Japanese R&D system, and the other reason is I don't know the English terminology, but there is a law to constrain the exchange of the parts or informations between the foreign countries. So we cannot specify what kind of informations are included in the systems. So many variety of data are included. So we need to specify the people who are living in Japan, Japan residents. So between the people in the Japan residence, this law doesn't matter. But yeah, this is technical problem.
Yeah. Thank you very much. I understand. And perhaps such, how do you say, boundary or the regulation restriction for the users will be important, because if this platform is open to everybody, then some user will feel worried for providing their own data to the system.
You're right. So we designed this what area or what kind of user can be applied very delicately, actually.
Thank you. Thank
Yeah.
you. Is there any other questions? Okay, so finally, I'd like to ask a more broader question. So what is your expectation and what is your prediction about the contribution data-driven research in the future, in 10 years, in 20 years, in 50 years?
Yeah. Okay. So yeah, my expectation is very simple. Maybe these all things will be such as Excel or something. So you use Excel daily to manage your data, to analyze the data, something, right? In the same way, you use PNAX as a daily tools. Other than that, it is impossible to how can I say, do the research. Maybe this is a kind of such an infrastructures for very simple.
Okay. Thank you very much. Is there any further questions? Okay, in that case, I'd like to thank Professor Demura again for a very new, very stimulating talk today. And also thank you for a very good discussion. And so I think it is a very successful first interest seminar series of I²CNER. I thank Professor Demura, and also I thank all the people present in this webinar. So I'd like to close this webinar now. Thank you, Professor Demura, again.
Thank you very much,
Professor. Thank you very much. Thank you very much, all the people. Thank you.
Thank you.